So today I'm going to talk about the research that I conducted. My research was broken down into 3 different chapters. My first chapter details a method that I developed to measure internal and external cavity dimensions to evaluate cavity suitability. That chapter has been published in the Wildlife Society Bulletin, so I won't be discussing that in detail on my method slide. I do have a link to the publication if you're interested in learning more about that. Instead, today I'll be discussing my study, which I developed that method for. And that was to evaluate wood duck or Ike sponsa cavity occurrence across various South Carolina types. So wood duck cavities have primarily been studied in the Midwest with a few studies in the Northeast, but there's little overlap with the tree species in these regions and what we have in the Southeast. In the Southeast, the studies completed are limited and pertain to either a single land ownership type, they're specific to one forest type, or they're general and don't pertain to cavities suitable for wood ducks. Without knowing where cavities occur, nest box programs have been established without an understanding of cavity availability. But what if we can uncover these common characteristics? Wouldn't nest boxes be best suited in areas that complement the occurrence of cavities rather than competing with them? With this inherent importance, why do we have this lack of knowledge? The simple answer is because it just is not easy. What do we have a lot of in South Carolina and in the Southeast? Swamps. I have no interest in climbing over 200 trees and waders after trudging through a swamp. So that's when I came up with the idea. I just was going to develop a method, and that way I could measure internal and external dimensions from the ground. And then I put it to work to investigate the occurrence of cavities and cavities suitable for nesting wood ducks with 2 objectives in mind. The first objective was to calculate the relative abundance of cavities and cavities suitable in the 5 most common forest types of South Carolina. And the second was to identify the tree and stand forest metrics that influence their occurrence. I am going to minimally discuss the first objective and my results from that just for the sake of time. My primary focus will be on that second objective. My hypothesis was that an increase in natural cavities will be found as stand age and DBH increases. And bridging this gap in knowledge is really vital to conserving and managing wood ducks and other cavity-dependent wildlife species, as well as informing forest management practices in this understudied region. My study area consisted of 2 site locations located in the Northern Coastal Plain Forest Survey Unit, which is the largest of the 3 units in South Carolina, and those are under the Forest Service's Southern Research Station. They're also located in the Southern Coastal Plain and Middle Atlantic Coastal Plain, and those are the level 3 ecoregions, which are highlighted in the pastel colors throughout all 3 of the extents. So you can see Francis Marion National Forest is cut in half between the 2 level 3 ecoregions. Francis Marion National Forest and Haugg Barony are managed by different landowner classes, but although landscape composition differs between sites, each is primarily comprised of freshwater wetlands, which is shown in blue, and forest, which is shown in green. And as you can see, there's a considerable amount of overlap. General wood duck nesting habitat is comprised of forested wetlands with trees less than 3.28 kilometers from water, with that water being greater than or equal to 8 centimeters deep in the spring. So pretty much areas with trees that are close to springtime, shallow water. All forested areas in our sample sites met those requirements. And aside from major water features, the terrain of both sites ranged from swamps to upland flats and ridges. And the climax community of this area, prior to European civilization, was a mixture of oak, hickory, and pine. I conducted my surveys from February to July 2022. I chose to evaluate the 5 most common forest types in South Carolina, so that way my prediction estimates could be referenced throughout most of the Southeast, but also I was able to maximize my sampling efficiency, not trying to do all forest types. But when narrowing them down, why would I include loblolly and longleaf plots? They're not necessarily raved about for being prime wood duck cavity locations, but I chose to because during my literature review, it was really hard to find a woodpecker study that didn't mention some kind of note about nesting attempts by wood ducks in cavities that were inactive and enlarged. That combined with loblolly and longleaf accounting for a majority of the forest in the state, I just didn't want to dismiss that as a potential factor that was unique to this region, especially with all the woodpecker activity and the expansion of their populations. So my plot center locations were determined using stratified random points in ArcGIS, and those are all the little red dots that you see, look like chickenpox almost. And I stratified points based off of stands greater than 50 years old. That was found to be the minimum stand age with cavities used by wood ducks by Gilmer et al. And Fan et al. I used 20-meter radius circular plots for my surveys, and I sampled at least 16 plots per forest type at each site. And there was a minimum distance of 50 meters between plot centers. I modeled my survey methodology off of Zlanis et al. So, that survey is with the Minnesota DNR. So the data collected could be used to predict the occurrence of tree cavities using remotely sensed data in the future, which is exactly what they did. It's an incredible study and very interesting for anyone interested in looking into that further. I based suitability parameters off of the minimum, excuse me. I based suitability off of the minimum and maximum parameters recorded in past literature for cavities used by wood ducks to ensure detection of potential cavities. So as you'll see, the minimum DBH for a suitable tree is only 22 centimeters. Once upon a time in literature, a wood duck was found nesting in a tree with a 22 centimeter diameter. So there you have it. That's what I used. To provide context, the cavity was located in a bowl in the tree. So the area where that bowl was 28 centimeters in diameter, but I wanted to keep it standardized, so I left it at that. Each plot and large tree was assigned a 5-digit numeric code. The first 3 digits were the plot number. The last 2 signified the tree location in the plot, starting with the northernmost tree and then continuing clockwise. I did that way so I only had to average waypoints and get a GPS point for the central plot location, and everything else was relative to that point. That saved a lot of time rather than having to average waypoints for every large tree. Cavities found were evaluated for suitability using the method I developed, and there's the link at the bottom. Cavities were defined as having entrance dimensions greater than or equal to 4 by 4 centimeters, and that was just simply the size of the head of the camera that I used in my method. Cavities were defined as suitable, meaning they met all conditions were met. Marginal, if one or more measurements couldn't be taken accurately, but they did clearly meet criteria. The couple that I noticed with the marginal, the cavity angle was just too great, so I couldn't get my internal measurements accurately, but I could tell that they met them. Unknown cavities were the ones I was unable to access, and the cavity was deemed unsuitable if one or more criteria were not met. Suitable cavities were defined as having entrances greater than or equal to 6 by 6 centimeter entrances. They had to be at least 10 centimeters deep, and platform dimensions had to be at least 14 by 15 centimeters. They also had to be without standing water or debris, and they couldn't be hollow to the ground. I measured dimensions in the order that they would be encountered by a wood duck hen, and I only recorded the reason for unsuitability for the 4 most disqualifying criteria. To analyze the forest metrics listed and detect their potential effect on cavity and suitable cavity occurrence, I used a generalized linear model. And following analysis, I used the significant variables and abundance estimates for suitable cavities to identify areas with higher probability of cavity occurrence and determine the number of 20-meter plots, each plot being 0.13 hectares in those areas. I did I do have abundance estimates and density estimates for all forest types at both sites, but I had to trim those down so I had enough time to get to what I want to discuss today. From February and to July 2022, I surveyed 166 plots and collected data for 4,633 trees. I identified 225 potential cavities, 156 cavities, and 31 suitable cavities. The top table shows that breakdown by suitability. Out of the 225, 28 ended up not being cavities at all, which gets you that 197. 41 cavities were classified as unknown, just due to inaccessibility. Out of those, 28 of them were too high due to the limitations of the method that I used. As shown in the bottom table, I found 126 unsuitable cavities, and I broke those down further by reason, whether it was the entrance, and again, this is the foremost as encountered by a hen breakdown. Of the 135 species of large trees that I identified, 24 species contained cavities and 15 contained suitable cavities. The highest rate of cavities was in green ash, and that was 33.3%. And the highest suitable cavity rate was in American beech, and that was 25%. This graph shows the 31 suitable cavities by tree species, which are along the x-axis, and forest type, which is indicated by the color / the design of the bar segments. Cavities occurred most frequently in swamp blackgum or Nyssa biflora and laurel oak. I found 18 cavities in the oakum cypress forest type, which is all of the blue, followed by 6 in oak hickory, which is in yellow, and 5 in oak pine, which is in green. Longleaf and loblolly pine stands each had 1 cavity, but the loblolly cavity shown here in red was in a red maple. It was not in a pine. These are the results from my generalized linear model with cavities on top and suitable cavities on the bottom. The best fit model for factors contributing to the occurrence of cavities showed a positive effect on cavity occurrence for the site index, DBH, and stand age, with a minor negative effect on tree density, for tree density. The best fit model for suitable cavity occurrence showed a positive effect for DBH and stand age, a negative effect for tree density, and no effect for basal area. Following my analysis, I plotted all of the trees by DBH, which is on the left, and stand age, which is on the right. The reason for the linear dots in this graph is because all of the trees in a given plot have the same stand age. So that represents the number of trees per plot. The average DBH was highest in oakum cypress, followed by oak hickory and oak pine. The DBH in longleaf and loblolly stands were 34.4 and 34.7 respectively, so very similar. The average stand age in oakum cypress plots was 118 years, which was higher than the oak hickory at 104 years, and oak pine, which averaged 92 years. With my analysis results, largely the abundance and the density estimates that I calculated, I used those with optimized hotspot analysis tool in ArcGIS to highlight areas with high and low suitable cavity probabilities. By symbolizing the output with a heat map, I was able to highlight cavity hotspots, which you see in red and yellow, with the cold spots in blue or no color at all. As a quick note, the distinction of the heat map is a lot more noticeable for Haugg, only because it's a much smaller size. If you went to the Francis Marion map and blew it up and zoomed in, it would look just like this if it was at the same scale. Hotspots signify areas with greater than 95% confidence for the occurrence probability of suitable cavities, and cold spots signify areas with greater than 95% confidence intervals for probability of no cavity presence. In the table on the right, I ran some more analysis in GIS, and I was able to figure out the number of 20-meter radius plots that can be done at these confidence intervals. So starting with 0, meaning lacking data, but it wasn't an absence area. If you add them all up, it came out to about 83,000 plots. 99% confidence interval, there was 4,500. So a lot of room for future research here. And by using this analysis, I was able to take my combined sample area at both of my sites and decrease it by over 85%. So in the future, I would only be able to look at areas that were likely to have suitable cavities. So early in my development of my project, I set out to structure my methods to form a unbiased baseline for cavity presence in the Southeast using all the data from past literature dealing with cavities that I could get my hands on. As a result, several random plot centers fell in very young stands that just met the cut, and a lot of those are shown here. Hopefully you can see I had to decrease the image quality, so I was able to stream this. So a lot of those surveys were done in, excuse me. Also, so a lot of the surveys were done in younger plot stands, and also I not only surveyed for wood duct cavities, but also cavities that were earlier in their development that had a potential to become suitable. So although the number of suitable cavities found could be thought of as minimal, it wasn't something that I was surprised at due to my unbiased approach. And instead, I just hope it serves as a guide to best direct future studies to areas of higher cavity probability without something coming up in the future and someone in the future researcher having to backtrack and go behind and start from scratch. I wanted to provide that baseline. Relative to the potential cavities that I discovered, my determination of 12% of potential cavities as suitable for wood ducts aligned with other studies. And I wouldn't be surprised if the deficiency was more a result of my learning curve in the beginning, as I was painstakingly figuring out what a cavity looks like from the ground. And I think my technician can attest that it was a hard and tiring lesson to learn, but we did learn it pretty quickly. I found classifying reasons for unsuitability to be noteworthy because of their potential to be suitable in the future. So while 31% of cavities were deemed unsuitable for standing water debris or being hollow and would remain unsuitable, the other 70% had the potential to be suitable as the cavity continues to expand. In Indiana, Rob also noted 226 cavities at his study site that had just started forming. Marking and monitoring these cavities that are early in developmental stages offers a unique opportunity to gain insight into cavity progression while also serving as a proactive approach to cavity identification. Even if only half of these cavities matured to be suitable between both of our sites, the sample sizes at our sites would more than double. So what makes these surveys so particularly worthwhile is the perseverance of cavities over time. And although several factors can affect the life of a cavity, Rob found the annual duration of suitable cavities in Indiana was 91.3%, which is extremely high. And he noted that lost cavities were comparable to the formation of new cavities. Belrose et al. Also collected data in that same study area as Rob, except he looked at it over a 22-year period and found that suitable cavity occurrence was stable over those 22 years. Roy Nielsen et al. Found the 10-year survival of suitable cavities was about 0.64. And between Robin Bookout and Yetter et al., annual survival ranged from about 0.89 to 0.99. The long lifespan of cavities only reinforces the practicality of conducting surveys, really despite the challenges. To give more insight on possible reasons for differences between forest types, I want to know if it was at face value. I don't want to take it at face value, so I dug into it a little bit more, and that's why I graphed them by DBH and stand age. Oak hickory and oak pine stands were not significantly different from oak gum cypress, but these graphs may provide insight to their potential to host natural cavities. Oak hickory stands, which fell second, and oak pine, which fell third, and their average stand age also fell second and third in cavity occurrence. The positive correlation between stand age and DBH and cavity occurrence suggests that surveying older hardwood stands with greater numbers of large DBH trees could increase sample sizes of cavities and help us parse out whether the forest type or characteristics are more influential. Historically, low densities of cavities occurred in the Deep South due to the absence of those northern tree species that are known to be cavity prone. And there is also the tendency for hardwoods to be cut before typical cavity formation occurs. This, I believe, may have influenced the belief that current generations have that the South lacks as many cavities. However, forest management practices have greatly improved, and the disturbance and the harvest of trees for southern forests has been reduced to less than 3%. And that only continues to increase the number of cavities as the age of those stands grow. So while it's too early to declare this fact or fiction, I just recommend future research so that way we can dig into it more. Through future research, we can increase our understanding of characteristics indicative of cavity occurrence and advance our understanding of cavity nesting wood duck reproductive ecology throughout the Southeast. Improved data will facilitate future research and updated forest management practices by classifying tree characteristics indicative of suitable nesting cavities, helping forest managers understand cavity tree location and abundance, and that benefits not only wood ducks, but all cavity dependent species. So I'll end by giving one last thank you to everyone involved in making all of this possible. The last 3 years have been incredible, and I thank everyone so much. And if I have any time left, I will take any questions.